Soft robots have the potential to be incredibly useful because they can bump into or push objects with any part of their bodies. However, controlling them is difficult because as continuum robots, it's difficult to represent their configuration in a realistic and accurate way. While we have methods inherited from continuum robots, they have difficulty representing the high localized deformation of the examples of wrinkling, pleating, and folding shown here. The DiscThread model of representing and simulating the dynamics of a soft robot doesn't discretize the partial differential equations of a continuum rod, but instead creates a lump parameter representation, discretizing the robot itself into a series of disks joined by threads. The relationship between the disks is specified by a series of 5 angles: alpha, beta, gamma, psi, and phi. To get an idea of the types of shapes changing these coordinates gives the robot, consider the slide shown here. In the first image, only the betas are non-zero. The rest of the generalized coordinates are 0. We do the same for gamma and phi in the next 2 images. The image at the bottom shows the configuration of all the betas, gammas, and phis shown above, all taking on those non-zero values at the same time. The idea described in the paper begins like this. If the disk marked in green is moving relative to the disk immediately before it, we can write the relative angular velocity in the coordinate system shown by multiplying the time derivatives of alpha, beta, gamma, psi, and phi for that thread by a matrix E that depends only on those 5 generalized coordinates. This is the same expression no matter which pairs of disks you are considering. So we can generate every relative angular velocity expression just by appending a subscript using a symbolics mathematics program. So now you may be thinking, we just need to form the kinetic energy expression of all of those values. Then we can symbolically differentiate, then symbolically take the time derivative of that, right? Absolutely not! The further we go distally, the longer and more wieldy the expressions get. We tried this. And here's a look at scrolling through the columns of the mass matrix, column by column. And what you might have realized is that's just for a single disk. Instead, we note that the partial derivatives of omega rel have a relative structure too. We can tabulate all these expressions just by symbolically appending them with a subscript. Based on these, and the structure of the robot, we can reason generally about the structure of the partial derivatives of the absolute angular velocities and tabulate what they are. From this table, we can form the analytical expressions for the velocities of the center of mass, the mass matrix, the gravity vector, the stiffness matrix, and so on. Then at runtime, these can be calculated at each time step using only a function evaluation and a few matrix multiplications, as illustrated by this block diagram. Let's take a look at the output of the simulation. The following examples show the integration of the equations of motion where the fabric reinforcement is a continuous strip along one side and the elasticity of the chamber is represented by linear springs positioned at 90, 180, and 270 degrees from the thread.